All right, the last thing we're going to look at in this chapter is colligative properties. Colligative means of the collective, meaning properties that depend only on the total number of particles. This is very important because if we think about total numbers of particles, our electrolytes are going to affect how many particles we have, and we really need to consider that. So let's start out and let's consider vapor pressure. If we take a compound or like water and we look at its vapor pressure, we're going to get a nice equilibrium. We're going to get water going in and going out, and we're going to find a vapor pressure. Now, if we put into it a non-volatile solute, non-volatile meaning no vapor pressure. This would be like salt or sugar. These things do not evaporate on their own. So if we have something with no vapor pressure and we put it in there, it will actually stop water from escaping. And because less water can escape, the vapor pressure of the total solution is going to go down compared to the vapor pressure of the pure stuff. So the vapor pressure of the solution will go down. It will be lower than that of the pure solvent. This does some very interesting things to our phase diagram. So let's consider that we have a normal liquid here, and we know it's normal because we have a positive slope. So if we have our nice positive slope and we think about this, so the first thing that's going to happen when we add ourselves, which this one is a non-volatile solute. Now, if the solute itself is volatile and they both evaporate, you have a cool, interesting distillation question out of organic chemistry, which we're going to leave for them. So if we have a non-volatile solute, it is going to lower the vapor pressure. If it lowers the vapor pressure, it's going to give us a lower line down here. Now note, it also lowers here where the solid and liquid are going to interact, and it gives us a line further to the left here. Well, what does this do? This takes and increases our boiling point, and we call that boiling point elevation. And this takes and it decreases our freezing point, and we call this freezing point depression. So our freezing point goes down, and our boiling point goes up, and our vapor pressure itself also goes down. We have equations. Quick note, we know about this. We know that if we have things like antifreeze, we're going to put antifreeze into our water in our car. We're going to do this to try to pull some of the heat off of the engine. And we certainly do not want stuff that evaporates easily. And we also want stuff that's going to affect the freezing point. We do not want to have water circulating around our engine by itself, because water freezes at 0 degrees Celsius. So if our temperature got lower than 0, the water around our car would freeze. When water freezes, it expands and it would crack the engine block of your car. So we put antifreeze in to drop this temperature and make it lower than 0 degrees Celsius so our car engine doesn't freeze. Now we have an equation that goes with putting non-volatile substances into our solution, and it says that the pressure of the solution is the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent. So let's say that the mole fraction of our solvent, what we had left of our solvent was, say, 70.75. So 75% by moles of what we have left is solvent. Our pressure of my solution is going to be 75% of the pressure of the pure stuff. Now we have to be given a lot of information to do this, because obviously this is temperature dependent, and we're going to need the vapor pressure of our pure solvent to do these problems. All right, so we have a solution made up of 100 grams of sucrose in 100 grams of water. We know our equation. Our equation is the pressure of the solution is equal to the mole fraction of the solvent, which is water, multiplied by the vapor pressure of the water. Now the vapor pressure of the water here is given as 31.8 millimeters mercury or torr. So to do this problem, we need the mole fraction. The mole fraction of water, we know, is the moles of water over the total, which is moles of water plus moles of sucrose, which is going to leave us with some math. 100 grams of water, we know the molar mass is 1 mole for every 18 grams. is going to give us 5.56 mole of water. If we have 100 grams of sucrose with a molar mass of 1 mole for every 342 grams, we're going to get a number of moles of this of 0.292. Now, note, sucrose is heavy. We have very much fewer number of moles of sucrose than we have of water. So if we plug this in, we're going to get a mole fraction of the water of 5.56 over 5.56 plus 0.292, and that is going to give us 0.95, which tells us here that after we do the math, that the pressure of the solution is going to give 0.95, the fraction that we have left, over 31.8, and that's going to give us a vapor pressure of the solution of 30.2 millimeters of mercury, or torr. So we have some equations. Vapor pressure lowering we just did. Boiling point elevation and freezing point depression. Now, all of these depend on the nature of the solution, not the solute. So we're going to have some constants in here. Our K sub B is going to be the boiling point depression constant. Our K sub F is going to be the freezing point depression constant. And these depend on the solvent. And you're going to have to look these up or they're going to have to be given. So here are our equations. Our change in boiling point, that's going to be our increase, is going to be I. I is going to tell us the number of particles, multiply the constant times the molality. And we're going to have the same similar thing for delta T sub F. Osmotic pressure. Osmotic pressure is equal to IMRT, where this is pressure. So R on this one is our gas constant, and that's going to be liters atmospheres per mole K. All right, when you need some of these constants and these values, and you're going to need a fair few things, you're going to need the regular boiling point for any solvent, you're going to need its K sub B, you're going to need its normal freezing point, and you're going to need K sub F. These are almost always done at 1 atm, and these are the normals. So if we consider down here and we look at water, we know that water boils at 100, it freezes at 0, and it's got two constants. It has got a K sub B, and it has a K sub F. Now note this has a negative sign in here. We're going to ignore that negative for a while. It just reminds you that the freezing point is going to go down. So there was one more thing on those equations, because we were given, for example, that delta T sub F, the change in freezing point, is equal to I times the molality times K sub F. K sub F we know depends on the solvent. M is the molality, which is moles of solute per kilogram of solvent, and now we need I. I is the Van't Hoff factor. Van't Hoff factor is the actual number of particles over what you started out with. So, for example, if you have sodium chloride we know dissociates into two ions. Therefore, its Van't Hoff factor is 2. Now, the values are a little off because sometimes they don't dissolve as well as we like. We're going to ignore the measured ones and we're going to use these guys right here. If you have a non-electrolyte, our Van't Hoff factor is always 1. If you have something like magnesium or calcium chloride, it's going to break apart into 3 particles, 1 magnesium and 2 chlorides, and our Van't Hoff factor is now 3. This is going to affect the freezing point, for example, 3 times more than that of glucose. Glucose doesn't make as many particles. So let's do a little bit of math. So if we take and we consider antifreeze, and we know antifreeze is a combination of ethylene glycol and water, and the question is simply, what are the freezing and the boiling points? So we've got 2 equations. We know that delta T sub F, which is the decrease in freezing, or the change in freezing, is equal to Im K sub F. K sub F is given, and delta T sub B is equal to Im K sub B. If we look at ethylene glycol is a hydroxy OH group, CH2, CH2OH. This is a molecule, and I is 1, right? It's only going to be different from 1 if it's ionic. So let's do some math. In order to get our freezing points, we have to get the molality. The molality is going to be moles of solute. Well, we have 878 grams. We know we have 1 mole for every 62.01 grams, which is our molar mass. And we're going to divide this by the mass of solvent in kilograms, 3.202 kilograms. And we're going to get a molality of this solution of 4.42, lowercase m. Delta T sub F, the change or decrease in the freezing point, is going to be 1 multiplied by 4.42 lowercase m molality multiplied by 1.86 degrees C per lowercase m, giving us a decrease of 8.22 degrees Celsius. Note, that is not the freezing point. That's how far it's gone down. The new freezing point is going to equal the old freezing point minus delta T sub F. Well, the old freezing point is 0, delta T sub F is 8.22, so our new freezing point of this solution is not going to be 8.22, it's going to equal minus 8.22 degrees Celsius. We could do the same thing for the boiling point, and when we do that, we're going to get a delta T sub B of 2.30. We're going to add that to 100, the normal freezing point, because it's going to go up, giving us a new freezing point of 102.3 degrees Celsius. So what we have here is a new freezing point of 102.3, excuse me, a new boiling point of 102.3 and a new freezing point of minus 8.22. We exploit this in the wintertime by using sodium chloride, or in this case up here, probably calcium chloride, as a de-icer. Now, calcium chloride, in terms of mass to mass here, is going to be much better at de-icing than sodium chloride, because calcium chloride is going to break into 3 particles and it's going to have an I equal 3 versus sodium chloride of I equals 2. So it's going to have a greater effect on the freezing point. We do this in control of ice on wings on airplanes or on ice on the roads. So let's play with this for a moment and consider if you're going to make yourself some ice cream. We want this to freeze at minus 10. We know that the new freezing point, minus 10 degrees Celsius, is equal to the old freezing point, 0, minus the delta T sub F, how much it went down, because the freezing point is going to go down. So it tells us that our change in freezing point is a positive value, because it's just a net change of 10 degrees Celsius. We know that for sodium chloride, I is 2. We're having an amount of our solvent of 2.50 kilograms. So we know that 10 degrees Celsius, our change in our temperature, is equal to our I, which is our 2, moles of NaCl over 2.5 kilograms of solvent multiplied by 1.86 degrees C per molal. And when we plug that in, we're going to get moles of our NaCl equal to 6.72. Well, if we have 6.72 moles of NaCl, we know the molar mass is 58.45 grams per mole, and we are going to have to add a total of 393 grams of sodium chloride for every 2.5 kilograms of water to get a new temperature of minus 10 degrees Celsius. Leaving us with our last colligative property. Last colligative property is osmosis. Osmosis is flow of solvent, and this is very important because the solvent is going to go through this semi-permeable membrane. Semi-permeable means it just has really small holes. Solvent is smaller than the solvated solute, and because the solvent is smallest, it goes through. The flow of this solvent to the semi-permeable membrane is called osmosis. The solvent will flow from where you have more of it, lower concentration, to where you have higher of it. Such an application could include the desalination of water. When the equilibrium reaches and the liquid stops flowing, the pressure required To stop this flow, before the equilibrium would be the osmotic pressure. And that's just how hard we have to take and push down on our liquid to stop it flowing through the semi-permeable membrane. So if we have a pure solvent and we have a solution, we know the solvent is going to be what flows, and it's going to flow until you get equilibrium. And if you want to stop it, you're going to have to apply the osmotic pressure. If you applied a pressure greater than the osmotic pressure and you pushed down harder, you could force the solvent back through. Again, the solvent is the only thing that moves. And when you do this, you do reverse osmosis. This is how desalination works, or one of the processes in which we could do desalination, simply forcing the water through a semi-permeable membrane out of the salt water. Now we can do math with any of these things. And one of the things that we can do with this is that we can do or use the osmotic pressure to calculate molar masses. Now we know the molar mass of something is going to be the grams over the moles. So for hemoglobin here, which is what we're doing, if we want the molar mass, we want 35 grams over the number of moles in this solution. So we're solving for moles. We are doing osmotic pressure. So we know that our equation is pi is equal to IMRT. So with this in mind, this is hemoglobin. So I is 1. How do we know I is 1? We know it's 1 because it's a molecule and it's not ionic. We know our temperature is 25 degrees Celsius, and this needs to be in Kelvin. So this is 298 Kelvin. And the R for this is the gas constant. How do we know? Because its pressure is going to be 0.08206 liters atmospheres per mole Kelvin. Okay, so we have our R, our temperature, and our I. We know the volume of the solution. Let's finish this up. Well, R over here, our pressure is in ATM, so we need ATMs here. So we're going to take our 10 torr. You know we have 1 ATM over 760, and that's going to give our pressure in atmospheres. Our Van Hoff factor is 1. Our molarity is moles of the hemoglobin for every 1 liter of solution. If our volume of the solution was different, we put a different number here, multiplied by the gas constant, 0.08206. I'm leaving off the units just for space, multiplied by 298 Kelvin. All right. When we do this, we are going to find that the moles of hemoglobin is going to work out to be 0.000538. So after we've got the moles of the hemoglobin, we want the molar mass. The molar mass is going to be 35 grams, which is given over 0.000538 moles. And you're going to get 65,000 grams per mole. And yes, that's the case. It's very heavy. So one of the things that's interesting about osmosis is when we look at our cells. Cell membranes are semi-permeable, and we've got to get water in and out of these all the time. And we have some definitions here. Isotonic means same. So isotonic solution has the same osmotic pressure as bodily fluids. Now note, bodily fluids have an osmotic pressure on the order of about 7.8 atmospheres. So if we're going to take and put something in a reaction or interaction with our body, we got to make sure that its osmotic pressure is the same. Hypotonic means lower. Hypo means less. So if the osmotic pressure of the solution that it's in contact with is less than 7.8, we have a hypotonic. And what's going to happen is, because it's going to flow from the dilute, which is the solution, into our cells are going to swell and potentially rupture. This is pronation. Hypertonic, hyper means higher, meaning that the solution is going to flow out of the cells into the solution around it. This is going to cause crenation or shrinkage due to net flow of water out of the cell. How might you see this? So let's look at some red blood cells. Isotonic. Our red blood cells have an osmotic pressure on the order of about 7.8. If we put them in a solution of 7.8, our water is just going to flow nice in and out at the same amount, and we're going to have an isotonic solution and nice, healthy red blood cells. This is, for example, if you had an IV of 0.9% mass to volume NaCl. This is the same kind of solution you would use to clean your contacts. That works out to have an osmotic pressure of about 7.8 atmospheres and is isotonic. If instead you took and you exposed your red blood cells to, for example, salt water. So if we take and we put it in seawater, seawater has an osmotic pressure of about 28 atmospheres. And because the concentration out here is higher than the concentration in there, you get a net flow of water out and you get crenation, where your red blood cells are going to shrivel and actually die if we, or get very badly damaged. If we have hypotonic and we just put our red blood cells in pure water, if we put red blood cells in pure water or you were given an IV of pure water, the water would flow into your red blood cells and they would explode, hemolysis. So we need to be very careful on what we put our bodies in interaction with as a function of their osmotic pressure, making sure it's the same as our red blood cells.